App testing go. As previously discussed, my at least like host-based application testing, not my favorite thing in the world, but hey, it might turn out that it is yours. So we will at least talk about it and my distaste for it. Man, the G-debugger, ugh, just ugh. All right, so static and dynamic application testing. We'll learn the difference, how to plan those out, and then how to use tools to help us get there. And then if you do want to do app testing, there's a beautiful grad course at Purdue that'll tell you, like, I did the overview of that. There's apparently a deeper dive app testing where you will be forced to do things like attack binaries that do stuff like address space layout randomization and have to use like, there's something called ROP gadgets? I forget. I was like, yeah, I'm out. This is driving me nuts. So when you're trying to figure out an application, you've got some options on how to go about that. You can start by reviewing the application sitting still, statically analyzing it. You can look at it as it acts by dynamically analyzing it. You can go through and try and reverse engineer it through decompilation, meaning you can take a compiled binary and try and revert it back to a decompiled state. You may be able to find vulnerabilities inside of particularly web applications just through scanning the application, and then stress testing, throwing a lot at the application and seeing if it breaks, and then security regression testing, going back through and looking at previous iterations of this thing. So a lot of this would involve like code review. So you do this the way you do all of, like, these should be integrated into most code development practices these days. Hopefully, like going through and analyzing how data flows through an application, creating graphs that talk about, we take user input here and then it goes into this variable, and then from this variable it goes over here and we do this thing to it to try and figure out what's going on, which can also lead to taint analysis, meaning based on where we took user input, which is not trusted, go through and analyze how things are done. And then you can also analyze the code itself to try and figure out what it is that the code do in order to figure that out. I think we have a little exercise where you will go through and do a little code analysis. But essentially you're looking for things like buffer overflows, where we write too much data into a memory address, which again is why I argue people probably shouldn't be writing in memory unsafe languages if they don't need to be. So like C++ is fast for sure, but you can sure shoot yourself in the foot in a lot of different ways. Or like we look at like use after free errors, where we freed up a block of memory, but somehow there's still an opportunity to use that memory to do something. Various like race conditions where you think you wrote, I have an alert showing up on one of the systems I keep an eye on because it sees the file it's checking as it starts checking, and then when it checks to see if root can access it, the file's already been deleted because it's a temporary file, and that race condition triggers an alert every time. Kind of annoying. So those are the kind of things you should do. And ideally, if like your business develops applications, you should have a software development lifecycle that includes doing that sort of work. So the planning phase for this looks like a lot of the other planning phases we've talked about. We go through and figure out what should be built into each checkpoint as we go along through whatever our system development lifecycle looks like. So if you're a waterfall shop where we have specifically defined objectives at each step in the waterfall, there should be some sort of testing that happens. As part of a Scrum lifecycle development where you do like sprints and iterate around and around. And this is the international symbol for agile software development, by the way, just like doing this number right here, because they iterate in little circles. Security should be integrated in before or as part of, as we go through, as we're doing user acceptance, where we're checking to see, hey, do our users actually understand how this works? Did we check, like, was security a part of that consideration? Stress tests, how well does it withstand, particularly, again, for like web apps, how well does it withstand 600 users banging on the system all at one time? And then if there were unplanned changes, we could go through and see if we could revert back to them in regression testing. So if you can't get the source code, which if you're external, you probably can't, the next best thing to figure out would be like reverse engineering it by decompiling it using a bunch of reverse engineering tools that are out there. But we had talked about Ghidra, I think you say Hydra, Ghidra, or IDA, and I guess you have friends who have the pro version. That must be nice. Or a couple of others. Software assurance programs, not exactly the same thing. Usually these are going to want to have access to your source code and figure out what's going on. A debugger, on the other hand, will go through and help you take a working piece of software and see what's going on the inside of it. If the developer of the software was kind enough to leave like the debug symbols inside of the application you're looking at, you will see things like function names and fun stuff like that. If they didn't, you're going to be guessing at what the debugger thinks they are. And having spent some time recently in Gdebug, like I was whining to the students in attendance here beforehand, not my favorite thing in the world. Looking at memory addresses and trying to figure out how to overwrite them. Fuzzing is an interesting software security concept, which is, it's basically, we go and we throw a bunch of crap at the application and see if it blows up. So like, we send random inputs and then we see what happens. And what you're looking for is a place where the application or the protocol or the application that accepts some kind of file blows up when we give it some type of information. So you can have a fuzzer firing away at a application. When the application crashes, ideally what happens is the fuzzer stops and says, hey, when I sent it this information, it blew up. Let's try that again. And it sends that same bit of randomness to it. And if it blows up again, you can say, aha, now we have found some place that causes a crash based on this input. Let's go and figure out why. And that is a way to find many a application problem. And fuzzing is actually becoming very popular. Our friends at VDA Labs were big into this. Jared DeMott, Dr. DeMott, who formerly of VDA Labs, now I think of Amazon, his jam was writing what are called harnesses for fuzzers. So the fuzzer generates the randomness, the harness makes it talk to the application. An interesting area of research. You can also use tools like Burp that are interception proxies. So it's like building your very own man in the middle. And so you set up a certificate from your Burp proxy. Actually, I think the last time I installed Burp, it didn't even need to go through the rigmarole of, like if you're running it on the same machine you were going to be running the web browser on, you didn't even need to set it up as it wasn't very hard. You just kind of hit go, and Burp had its own browser and everything into it. One of the ways it can work is you would set up a proxy that's going to intercept. So you've got your Burp proxy running here, and you give a certificate, that's my international symbol for certificate, to the client over here, and then your proxy gives a certificate to whatever the web app is over here. And you sit in the middle, and even though both parties think they're having a secure communication, they're actually both talking to the proxy, and the proxy is intercepting all of the traffic over there. So I guess this could be Alice, and this could be Bob, and this could be Eve, intercepting, person in the middling the whole thing. So the idea is you can see not even necessarily the browser. I did this for a game that was just using HTTPS to talk. So anything that has a protocol you can intercept, you can start looking at the traffic and start reverse engineering and figuring out what's going on. So if you want to know why you only get 10 gems every day, you probably violate the terms of service for the game by doing so, but you could go through and look at what happens when you start feeding interesting and different data to those sorts of things. So those are Zap does that, Burp does that. There's a bunch of other ones out there that perhaps not as popular. And then a new concept in like rapid system deployment and the whole like continuous integration philosophy of developing applications, kind of driven by the ginormous sized organizations, is this concept of containerization or operating system level virtualization. But containers are like, if you're familiar with like level 1 and level 2 hypervisors for virtualization, right? You've got level 1, which are like hardware, the hardware is just doing virtualization. Level 2 would be like an operating system running, your system's running VirtualBox. Or like the hardware level would be our lab that has ESXi servers that all they do is virtualization every day. And if I restart my computer, I'll probably even be able to talk to them. But for whatever reasons, my VPNs like to get confused with each other. So that's, you know, standard virtualization you're probably familiar with. Containerization takes it, so like this is, you know, you've got your hardware at the lab, it's running the ESXi hypervisor, and then you've got virtual machine 1, you've got virtual machine 2, you've got virtual machine 3. And sort of the hassle for that is, now I'm running an operating system on each one, and those operating systems suck up a lot of resources, especially if they run Windows, and not great, right? So you've only got so much hardware on this physical machine here, and you're chewing up a bunch of it to run what might be exactly the same operating system 3 times. And some of the actual like smarter virtualization platforms will share like libraries and memory addresses across duplicate operating systems. But containers abstract that away even further. So now you've got like your AWS server here running your Linux operating system on top of it with a containerization tool, like Kubernetes is a popular one. And there's a handful of others. And instead of having individual operating systems, now you will just have one operating system, and then the unique binaries and libraries, which like is why you have Linux distros, is why you have operating systems, because keeping the appropriate binaries and libraries for an application together are a huge pain in the butt. So just distributing a container that includes the application itself and then any of the software the application it depends on is kind of a nice way to run a software distribution. So when I need a new version of whatever is in container 3, they just give me the whole container, and I don't have to worry about if the library I have is out of date. It just works. Excuse me. And it doesn't interfere with container 2 if container 3 needs version 4 of this library and container 2 needs version 1. So it's super handy if you want to move applications around. And if you have a container for, like if you were AWS, or no, if you were like Netflix, and I spin up a container so that I can look at a movie, you can make 1,000 of those scale up, and then using a service like AWS where it's elastic, you can have 1,000 of those containers appear, and then you can have 1,000 of those containers disappear when you no longer need them. And it like shortens the life cycle that the security people have to worry about, which is kind of nice. And it lets us have that application show up wherever we want without needing to like apply it over and over and over again, and make sure like all the libraries are there and all the other stuff that makes running a application on a Linux system, or any system for that matter, kind of a pain in the butt. So again, that's like a super high level overview of application testing. It is the sort of thing that merits several years of programming experience and then an application security class. But an interesting aspect of security. And we talked, like, focused on the binary sort of local application security, but there's also that web application security, which is actually kind of where I feel more comfortable. I teach web app development, so it's like I'm happier hacking on something through Burp Suite than I am trying to reverse engineer it with GDB and stuff. I totally was going to say stuff. All right, last quiz for the day, and we'll get you guys out of here. So the development team created a control flow graph for a new application. Where are we in development? I think we only talked about one of these, so.
Is it D?
Yeah. They're statically analyzing their code, looking at how the things work as it progresses through it. How about we've just rebuilt the back end of an application to boost server performance and you're ready to test the new version. What kind of test would we figure out if we found any problems with the existing security features? What kind of test would discover if the changes caused any problems with the existing security features? So the stuff that was in there before, did we break any of it?
B, a regression test?
Yeah. And we kind of like glossed, like we only hit this at a high level, but like Microsoft has had like huge vulnerabilities come back because somebody updated the software with like an old repository. And the next thing you know, we've brought back the vulnerability from 2 versions ago. All right. Whoa, which of the following statements are true of both decompilers and debuggers? They are DAS tools, they are SAS tools, they execute programs inside of controlled environments. You can use them when you don't have access to source code, or you can use them to generate human-readable source code. Both decompilers and debuggers. And
D is correct.
Correct. And we did not mention that dynamic application security testing is often called DAST, and static application security testing is often called STAST. And since it's a choose all that apply, and I took the time to explain that.
A?
A. Yeah.
Guys are good. Oops. Don't look at the bottom of the screen there. You want to test a web application, but your browser limits your ability to tailor the precise input you send to the server. What kind of tool would allow you to create specific HTTP requests that your browser will not? A debugger, a fuzzer, an interception process, or a proxy, or a taint analysis framework?
Is it C?
It is like Burp Suite. Yeah. You want to perform source code analysis of applications written under a variety of language, but you'd rather not learn multiple programming interfaces. I know that feel, bro. We glossed over these. Which would be the best response? Would probably be Sonar Cube that happens to do that. So I guess worth reading through all of the descriptions in the book about which does which. Which of the following is not true of container virtualization? Choose the best. Agent-based scanners are better to evaluate container security than network-based scanners. Not true. Containers are more isolated from each other than VMs. More containers than VMs can run on the same hardware. Since containers are a newer technology than VMs, many administrators are unfamiliar with their security needs, which is not true.
B.
Yeah, they are not more isolated from each other than other VMs because they share an underlying application. They share an underlying operating system. All right, whew, that's active recon. So hopefully you at least have a list of the commands you can use to do nmap and hping. We've got some idea on how we'd plan vulnerability scans, how to test new applications. We've at least heard of static and dynamic analysis, decompilation, debugging, and fuzzing, and all those things.